Lesson: Recurrent Neural Networks, RNNs, and Long Short-Term Memory, LSTM. Recurrent neural networks and long short-term memory networks are pivotal in the landscape of neural networks, particularly for their ability to process sequential data effectively. These advanced neural network architectures are designed to address the limitations of traditional feed-forward neural networks when dealing with sequences of data, making them essential tools for tasks such as language modeling, speech recognition, and time series prediction. By understanding the mechanics and applications of RNNs and LSTMs, AI professionals can significantly enhance the efficacy of their models in real-world scenarios. RNNs are a class of neural networks where connections between nodes form a directed graph along a temporal sequence. This architecture enables them to exhibit dynamic temporal behavior, making them suitable for tasks involving sequences. Unlike feed-forward neural networks, RNNs can use their internal state to process sequences of inputs, which is crucial for tasks where the context or sequence of inputs is vital. However, a major challenge with standard RNNs is the vanishing gradient problem, which hampers their ability to learn long-range dependencies. This issue arises because gradients used in training through backpropagation tend to diminish as they are propagated backwards through time, leading to ineffective learning of dependencies that are distant in the sequence. To address this limitation, long short-term memory networks were introduced by Hochreiter and Schmidhuber in 1997. LSTMs are a type of RNN architecture specifically designed to combat the vanishing gradient problem. They achieve this by incorporating a memory cell that can preserve information over long periods. The LSTM architecture includes 3 gates: input, forget, and output gates that regulate the flow of information into and out of the cell. This gating mechanism enables LSTMs to maintain and update their memory selectively, thereby learning long-term dependencies more effectively. In practical applications, LSTMs have been widely adopted across various domains. One notable example is their use in natural language processing tasks, such as machine translation and sentiment analysis. NLP tasks often involve understanding the context over long sequences of text, which LSTMs are well suited for. For instance, Google's neural machine translation system incorporates LSTMs to translate text with high accuracy by capturing the context of entire sentences rather than translating word by word. This approach has led to significant improvements in translation quality, highlighting the practical impact of LSTMs in real-world applications. Another area where LSTMs excel is in time series forecasting. Businesses rely on accurate time series predictions for various functions, such as inventory management and financial forecasting. Traditional statistical methods often struggle to capture complex patterns in time series data, especially when dealing with nonlinear relationships. LSTMs, with their ability to model long-term dependencies, provide a powerful alternative. For example, LSTM-based models have been successfully applied in predicting stock prices, where they can capture intricate temporal dependencies that influence market trends. Implementing RNNs and LSTMs effectively requires familiarity with practical tools and frameworks. TensorFlow and PyTorch are 2 of the most widely used libraries for building and training deep learning models, including RNNs and LSTMs. These frameworks provide comprehensive support for defining complex architectures and optimizing them with efficient algorithms. In TensorFlow, for instance, the Keras API simplifies the process of building LSTM models. With just a few lines of code, professionals can define, compile, and train LSTM networks, enabling rapid experimentation and deployment. Consider a practical example of building an LSTM model for sentiment analysis using Keras. The process begins with data preprocessing, which involves tokenizing text data and converting it into sequences that the model can process. Next, an LSTM layer is added to the model, specifying the number of units and the input shape. The model is then compiled with an appropriate loss function and optimizer, such as categorical cross-entropy and atom, respectively. Finally, the model is trained using the prepared dataset, allowing it to learn the underlying patterns and make predictions on new data. This step-by-step approach demonstrates the actionable insights that professionals can gain by leveraging modern frameworks to implement LSTM networks effectively. Despite their advantages, LSTMs are not without challenges. One of the primary considerations is the computational cost associated with training complex LSTM networks, especially with large datasets. This is where the concept of model optimization becomes crucial. Techniques such as model pruning, quantization, and the use of specialized hardware can accelerate training and inference, making LSTMs more feasible for deployment in resource-constrained environments. For instance, using TensorFlow's model optimization toolkit, professionals can prune unnecessary weights from an LSTM model, reducing its size and improving inference speed without significantly impacting accuracy. In addition to these optimization techniques, understanding the nuances of hyperparameter tuning is essential for maximizing the performance of RNNs and LSTMs. Parameters such as the number of layers, units per layer, learning rate, and dropout rates can significantly influence the model's performance. Tools like grid search and random search can be employed to systematically explore the hyperparameter space and identify the optimal configuration for a given task. Furthermore, automated machine learning frameworks, such as AutoKeras, can streamline this process by automatically searching for the best model and hyperparameters, reducing the time and expertise required for model tuning. Pause. To illustrate the impact of effective hyperparameter tuning, consider a case study in the domain of speech recognition. Researchers conducted experiments comparing different LSTM architectures and hyperparameter settings to optimize performance on a speech recognition task. By systematically exploring various configurations, they achieved state-of-the-art results, reducing the word error rate by a significant margin compared to baseline models. This example underscores the importance of hyperparameter optimization in achieving superior model performance. In summary, RNNs and LSTMs are indispensable tools in the toolkit of AI professionals, offering unique capabilities for processing sequential data. Their ability to capture temporal dependencies makes them highly effective for a wide range of applications, from natural language processing to time series prediction. By leveraging modern frameworks like TensorFlow and PyTorch, professionals can implement these networks efficiently and effectively. Moreover, understanding the challenges associated with RNNs and LSTMs, such as computational cost and hyperparameter tuning, equips practitioners with the knowledge to optimize models for real-world deployment. Through practical examples, case studies, and actionable insights, this lesson provides a comprehensive understanding of how to harness the power of RNNs and LSTMs to tackle complex AI challenges and enhance proficiency in the field.